Hey everyone, I hope the math classes have been going well, I hope all your other classes have been going well, and I hope you're excited for the end of the year. But of course, just a little bit more work to do before the end of the year. So what we're going to do is, in this video, I'm going to go over the answers to your worksheet, and then I'm going to make another video to go over the answers of your test once you guys have done your test, and then we will figure out something for the final exam. I'm going to write that up, and we're thinking of doing your final exam in your math class on Monday the 28th, so that I can mark them Monday night and Tuesday night and then get them back to you just before you guys are out for the summer. So, without further ado, I'm going to get started on the answers to the questions, which I have here in front of me. So, again, if you guys have any questions about what's been covered, either in the worksheet or very recently in our differential equations unit, you guys can send me an email or leave a comment in one of the videos. But yeah, without further ado, let's get started. So the first few questions are asking for the slope of a given function. So your first function is y equals 3x plus 16. Am I right? Yes. All right. So hopefully you guys remember that a line, this is a line, and it's of the form y equals mx plus b, where b is the y-intercept and m is the slope. All right, so that looks like a b, slope. So, based on this formula right here, you should be able to figure out that the slope is this 3 right here. So your answer to this question should just be m, or the slope equals 3. All right. Now, a little bit of a refresher. Actually, you guys have to find the slope and the y-intercept, excuse me. Find the slope and y-intercept. Find the slope and y-intercept of this function. So, hopefully you guys remember that if you have a Cartesian plane, you've got, actually hang on, alright, so I'm going to erase this and then we will draw the Cartesian plane and then we will get your answers sorted out. So if you have your Cartesian plane with your x-axis and your y-axis, then if you have a line something like this, let's say, then your y-intercept is where the line meets the y-axis, alright? I don't know if you can see better that way or this way. I'm going to leave the light off. So, where the graph intersects with the y-axis, where the function intersects with the y-axis, that's your y-intercept, and then the slope is the amount it goes up divided by the amount it goes over. Rise over run. We talked about that way back in January. And so it's the change in y divided by the change in x. And we'll get to that in a couple of questions' time. But for now, the easy way to remember it is with the formula y equals mx plus b. So m is the slope and b is the y-intercept. So based on that, where did the question go? Yeah, okay. Yeah, so based on that, your slope is 3 and your y-intercept is 16, just based on the function. All right? So let's move on to your second question. Here we go. Y equals 22x minus 1. Is that right? That looks right. Okay, again, same equation. Y equals mx plus b. M is the slope, b is the y-intercept. Just compare the two equations. The one with the x attached to it, the number in front of the x is your slope, and then whatever is tacked on at the end is your y-intercept. Now be careful, the standard equation says plus b. So if you have a negative number here, that would be the same as saying, instead of 22x minus 1, you could also say 22x plus negative 1. And then if you compare the two equations now, you'll see that b includes the negative sign. So you'd have to say that your y-intercept, or b, is equal to negative 1. All right, remember the negative sign. All right, so it's not just 1, it's negative 1, and that will make a difference in your graph. All right, next one, I threw a little bit of a curveball at you. This one is y equals 4 minus 12x. All right, so now for this one, I have written this equation a little bit out of order because the term with x in it is all the way at the end. And so I need to rewrite this as negative 12x plus 4. All right, I'll give you guys a minute to look at that if you need to. But negative 12x plus 4. The negative sign here needs to stick with the 12, and then you have a plus 4 at the end. Plus 4 because there's no negative sign out in front. And now it's the same form as the standard equation. So that means your m is right here. This is your slope. M is negative 12. And then your y-intercept is positive 4. All right, hopefully that's making sense. Whoops. If I'm going too fast, just rewind. But now we sort of change gears just a little bit, and we're going to find the slope a bit of a different way. All right, so now we're going to find the slope given 2 points. Given 2 points. Oh boy. All right, find the slope given 2 points. So I've given you point 1 is 6, 0, and point 2 is 12, 2. All right? Now remember, slope, m, is equal to the change in y divided by the change in x. And I think we briefly talked about the mathematical notation for this, and the way you write change in is with this triangle symbol called delta. So you have delta y divided by delta x, and that means change in y divided by change in x. Now the way you can write that is also the change in y is like if I asked you find the change in the temperature, find the delta temperature, then you would check the temperature at the start, let's say at 5 o'clock, and at 6 o'clock, and then you would tell me the change in the temperature between 5 o'clock and 6 o'clock. So you measure the start at the and the end, and then you tell me the difference. So you can say that the slope is the start to the end, or the way it's normally done is you measure the start and the end, and then you do the second minus the first. All right, hopefully you guys remember this from January. The second minus the first. All right, so if I said find the change in the temperature between 5 p.m. and 6 p.m., you'd tell me how much it changed. Let's say the temperature increased by 3 degrees. So let's say it was 27 degrees at 5 p.m. and it was 30 degrees at 6 p.m. for some reason. Then you would tell me that the temperature has gone up by 3 degrees. That means you did 30 minus 27, all right? So remember, it's y2 minus y1 when you do this change in y. It's the second one that you write first, all right? And same thing with the x's. x2 minus x1. If you did x1 minus x2, your answer will be negative, all right? So be careful, because you don't necessarily want that negative sign. It'll throw off your answer, all right? So be careful of that. Now, change in y, y2 minus y1. Remember that these points are written in the form x, comma, y. So y2 is 2, all right? And y1 is 0. So y2 minus y1 is 2 minus 0, all right? So that's just 2. And then x2 minus x1 is 12 minus 6. 12 minus 6 is just 6, so that's 2 over 6, which is the same thing as 1/3. All right? Awesome. Hopefully this is all making sense. We're going to do another example of that. 2 more examples of that, actually. All right, next one. I'll leave all the rest of that up. Next one. Point 1 is 2, 4, and point 2 is 18, 6. All right, so you're going to use the same formula. You have 2 points, so that means you have enough information to fill in all 4 of these numbers right here. All right, you have enough information to fill in y1, y2, x1, and x2. All right, y1 is 4, y2 is 6, so you do y2 minus y1, 6 minus 4 is 2. And then x2 minus x1, 18 minus 2, that's 16. Note that if I did 2 minus 18, if I did x1 minus x2, I would get negative 16. We don't want that, right? So be very careful when you're doing that, all right? So you get 2 over 16, and again, you can reduce that fraction to 1 over 8. If on a test or a final exam or whatever, you leave it as 2 over 16, I'm not going to take off marks for something like that, because I know you know what you're doing. And if you can reduce it to 1 over 8, that's great. But if I gave you a fraction that doesn't look like it reduces so easily, then don't worry about trying to reduce it, all right? But if it's something like 2 over 4, then hopefully you guys will see that that's the same thing as 1/2, and then you can reduce that, or in this case, 2/16, reducing to 1/8, something like that, all right? So we got one more slope-related question here. All right, so first point is 1945, and our second point is 33. 33, yeah, 33:45. All right, now remember, y is the change in y is the change vertically, all right? So the slant of the graph, and then the x tells you how much distance you have to go across to get that vertical change. Now if you look, y2 and y1 are the same thing. They're both 45, right? They're both 45. And so what that means is the change in y is 0, right? 45 minus 45 is 0. Now the change in x, we can calculate it. It's 33 minus 19 is going to be 14. But any number on the bottom here would still make this fraction come out to exactly 0. And what that tells you is no matter what 2 numbers go here for x, if both y numbers are the same, the graph is a straight line. The graph would look like this. You have your axes like that, and then your graph is just a straight line all the way across. All right, so you could have your x1 and x2 give you points here, or you could have your point go over there or over there, and they're all gonna just give you a straight line. All right? All right, now we change up the questions a little bit. Now we're not talking about slope, we're talking about different types of functions. We didn't spend a ton of time talking about this, so this might be a little bit on the tricky side, but hopefully not too bad. All right. So, how many bumps, this was the way I worded the question, how many bumps or changes in the graph going up to going down or the other way around appear in a quadratic function? So first things first, what do I mean about bumps? So when I say a bump, I'm talking about something like if I had a function that looked like this. All right, if I had a function that looked like that, and it's got some like weird like camel hump thing going on here, right? So then I would say this is one bump, this is a second bump, and this is a third bump, and this is a fourth bump. All right. So there's a bump right here where it's going up, going up, going up. Right here it's going up, and now it's going down. So right there is a bump. Here it's going down, and here it's going up. So in the middle, there's a bump. All right, so that's what I mean when I say a bump. It's going up to going down. That change from going up to going down or going down to going up, there's a bump right here, right here, right here, and right here. All right, so this example that I've just drawn here has 4 bumps. All right, but I asked some specific types of questions. How many bumps appear in a quadratic function? That was the first question. Now, hopefully you guys remember what a quadratic function looks like. It's one of the functions that's got, I'm going to write that up over here somewhere. Y equals ax squared plus bx plus c. All right, that's the standard form of a quadratic function. All right, and a quadratic function, our standard quadratic, looks something like this. All right, that should be touching the axis, but a standard quadratic looks something like that. All right, and if you can see, the graph is going down, 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 up, 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 right? So that means there's one bump right here. And any weird stuff you do with these numbers, a, b, and c, as long as it's still of the form something x squared plus something x plus c, like another number, then all that's doing is changing sort of the shape of this graph. So instead of looking like this, maybe you'll get one that looks really thin, something like that. Or you'll get something that's upside down or really wide, something like that. All right, and it could be up, down, left, right, all over the graph, all over the Cartesian plane. And so that's what changing the numbers will do for you. But if you notice, there's still one bump, one bump, one bump, one bump in all of these examples. A quadratic function has one bump. All right? Now I want you to notice the highest power of x, so the highest exponent on an x for a quadratic is a 2. All right? X squared. And it has one bump. So it's got an exponent of 2 and one bump. And we'll see how this factors in for our next question. All right? It's got an exponent of 2 in its highest power of x, but only one bump. Now our next one is talking about a quartic function. And so a quartic function looks like this. Ax to the 4th plus bx cubed plus cx squared plus dx plus e, where all of these a, b, c, d, and e are numbers, and that e is not the exponential that we talked about. It's not that 2.71828 number. All right. So this is the form of a quartic, and I'll draw an example of a quartic, and then I want you guys to see if you can figure out the bumps. All right. So here's an example of a quartic. All right, something like that. I'm gonna fix that end. All right, let's say something like this. That's an example of a quartic function. All right, and it just goes down to infinity there. Okay. So it's got a power of 4 on its highest power of x. The exponent is 4, and if you look, it's going up, up, down, down. So that means there's a bump in the middle, and then here it's going down and then up, meaning there's a bump in the middle, and it's going up and then down, so there's a bump in the middle. All right, so it's got the highest power of x is x to the 4th, and it has 3 bumps. All right, so the answer here is 3. So notice the pattern. It's got one less bump than the highest exponent. All right, one less bump than the highest exponent. So that's an example of a quartic function. And so you guys can hopefully, if you spotted this pattern, you guys can get the last one no problem. The last one is a cubic function, where you just kind of get rid of this x to the fourth term, and now you've just got x cubed, x squared, x, and then just another number at the end. This could be a, b, c, d, b, c, d, e, like I have here. Could be, I don't know, q, r, s, t. You could do whatever you wanted, really. So these letters in front of the x's are just any number, all right? And an example of a cubic would be something like this. So that's an example of a cubic. Goes down to infinity there, up to infinity there. All right? And if you look, the graph is going up and then down. So there's a bump in the middle. And then the graph is going down and then up. So there must be a bump in the middle. Highest power of x is x cubed, so the exponent is 3. Highest exponent is 3, and there are 2 bumps. And that's it. That's all there is to it. How many bumps appear in each of those functions? Just one less than the exponent. So if I gave you a function that was like y equals x to the 10th, then that means the graph of it will have 9 bumps. All right? So that's all that means. All right, next question. What are 2 helpful ways to remember which sides of a triangle are associated with sine, cosine, and tangent? All right, so you've got a triangle like this, and your angle theta right here. And I was asking, if I say find sine theta for me, cosine theta for me, and tan theta for me, there's 2 different ways we talked about. One of them is the easy, well, I mean, I guess neither way is overly difficult, and you guys seem to enjoy my way more. But, so here's your triangle, and you can do that you've got, so this would be the adjacent side, because this side over here is the opposite side, and this is the hypotenuse over here, right? The opposite side because it's nowhere near the angle. The hypotenuse is the longest side of the triangle, the one that's not touching the right angle over there, which leaves the adjacent side to be the one that's not the hypotenuse and is one of the other sides that's actually making up this angle right here. All right, and so based on that, we use the first letter of each of these to get S, C, and T, and then we just made an acronym out of it, S-O-H. So that's sine is opposite over hypotenuse, cosine is C-A-H, adjacent over hypotenuse, and then tangent is opposite over adjacent. And so the short form that a lot of people will learn is SOHCAHTOA or SOHCAHTOA. All right? Now, there was one other way that you guys learned, which I showed you, and I was surprised to see that you guys liked this way better. And instead of calling it adjacent, opposite, and hypotenuse, we called this side here the base, this side the perpendicular, because it's perpendicular, and this side we still called the hypotenuse. And based on this, we had the sentence, some people have, I'll write this down, some people, some people have curly brown hair through proper brushing. And how does this help? Well, S, C, and T are still standing for sine, cosine, and tangent. All right? S, C, and T are still standing for these right here. People have, P-H. Some people have, P-H. So sine is the perpendicular over the hypotenuse, right, which is the same as the opposite over hypotenuse that we had before. Curly brown hair, cosine, base hypotenuse, base over hypotenuse, through tangent, proper brushing, PB, perpendicular over base. All right, and those were the 2 answers. All right? So SOHCAHTOA was the easy one, or I guess the shorter one, and then the one you guys seem to enjoy more was some people have curly brown hair through proper brushing. Now do be careful, if this angle theta was up here, then this would be the base, this would be the base, and this over here would be the perpendicular. Alright, so it would look a little bit weird because now the side that looks like it's the base of the triangle is now standing over here and the perpendicular is down here. So just be careful of the naming of that. I'll try not to trip you up when I make your final exam. I'll try and be nice to you guys in that respect at least. Alright, so we'll move on from defining sine, cosine, and tangent, and we'll move on to finding some easy-ish values. Alright, sine of 30 degrees. The reason I say easy-ish is these are coming from your table. So make sure you review that table, practice that table, try and memorize the patterns because you might need it on your final exam. Alright, I haven't decided what exactly is going to go on it, but I think based on how you all did with finding these specific values of, like, you know, sine of 60 degrees and you know, cotangent of 45 degrees, learn and memorize that table. Hopefully you guys still remember it, but if not, go back and review that table, and that's why I've put up some of these questions over here. Alright, you guys should have it in your notes. If I have time, my assignments have been picking up a lot recently, but if I have the time in the next few days, then I will make a brief video just recapping that table and the rules of that table. I know you guys have done it already, but we'll see. Alright, so these are your 3 trig questions before we move on to derivatives. Sine of 30, hopefully you guys have got it from your table, but the answer is 1/2. The sine line you did have to memorize, and this was the second value. It goes 0, 30, 45, 60, and 90 degrees. Sine of 0 is 0, sine of 30 is 1/2. Alright? Cosine of 45 degrees is 1 over the square root of 2, or maybe you guys remembered this as square root 1 over square root 2. Is that how I did it? Yeah, I think I did something like that. Or oh, no, I did this as square root 2 over square root 4 is how I did this. Right? Square root 2 over square root 4, and this was square root 1 over square root 4. If that was how you memorized the sine line, the whole sine line, instead of being 0, 1/2, 1 over root 2, root 3 over 2, and 1, you could remember it as root 0 over root 4, root 1 over root 4, root 2 over root 4, all the way up to root 4 over root 4. Alright? So that's that. And then tangent of 90 degrees. Remember, tangent is the sine of 90 divided by the cosine of 90 will give you tan of 90. Sine of 90 is 1. Cosine of 90 is 0. But you can't divide by 0, so we say undefined. Alright? Or UND for short, if you don't have much time. Alright? So, undefined. That's it for the rest for those trig questions. For your final exam, I might throw a couple from the secondary trig functions like secant, cosecant, and cotangent. But if I'm asking you questions like find the sine of this, then I'll probably stick to just these sine, cosine, tangent, because you work with them a lot more. Alright, now I believe everything that's left is just derivatives and antiderivatives. This is going to go a little bit over 30 minutes, but hopefully you guys can get this. We did do this fairly close to the end, but I'll go over all of these anyway. So what is the derivative of y equals 3x squared? So if you remember your power rule, you bring the exponent down, multiplying it in. So you get this 2 down in front, you multiply it by the 3. So you get 2 times 3x. And then instead of a 2 up here, instead of having a 2 up here, you decrease the exponent by 1. So you have 3x to the 1. And if it's just a 1, you don't need to write it in. So you get 2 times 3x, which is 6x. Hopefully no problems there. All right? Okay, your next one is the derivative of 24x to the 4th. All right? Again, multiply this 4 down in front. 4 times 24 is 96. I won't give you such big numbers on your final exam. I want the multiplication to be easy. All right? X, and then decrease the exponent by 1. This time we do have to write it in because it's not just a 1 that we're left with. 4 minus 1 is 3, so we're going to have a 3 in the exponent. 96x cubed should be your final answer there. All right, stepping it up a little bit. Next one is 12x cubed plus 32x, right? Plus 32x. Yes, all right. So, same thing. You multiply this 3 out front, and you get 3 times 12, which is 36, x, and then you decrease the exponent by 1, so instead of a 3, it's just a 2, and you have 36x squared plus, and then the derivative of 32x, if it's just an x without anything else, like without a higher power of x, the derivative is just the number in front. So you could think of this as 32x to the 1, multiply the 1 out in front, doesn't change anything, and then that 1 becomes a 0, and your x term goes away. So this is just 32 on the end, and that's your whole answer. All right, now, one that has tripped you guys up a lot before, but hopefully you remember now, e to the x. Y equals e to the x. The derivative of this is the same thing, e to the x. Now remember, technically the derivative is e to the x times the derivative of the exponent, right? So if this was something besides x, then you would have to multiply by that outside, right here, all right? And that's actually what I was trying to get at with your next question, which is, what is the derivative of e to the 2x? Now it's going to be the same thing, e to the 2x times the derivative of the exponent, and the derivative of just 2x is 2. So you get this 2 out in front right here, okay? And that's the derivative there. Now the next one might have looked like a typo at first, but what is the derivative of y equals ex? Now e, this is Euler's number, 2.718281828 something something something, or you could even just think of this in this case as any number really. The idea is the same thing. The derivative of a number times x. This could have been pi if I wanted it to be, but the point is that it's a constant, all right? So this is a number times x. The derivative is just the constant in front, all right? Now, we're going to move on to antiderivatives, all right? So the basics of integration. And there's just a few of these, and then we'll be done. I am a little bit over half an hour, but hopefully you guys get enough time to watch these. All right, so antiderivative. What is the antiderivative of x squared? Now remember, for derivatives, I remember this was a little bit hard to kind of switch gears for. Remember, for derivatives, you multiply this exponent down in front, and then you decrease the exponent by 1. So you have to go completely in the reverse order. You multiplied and then subtracted, so now you have to add and then divide. So instead of subtracting 1, we're going to add 1. 2 plus 1 is 3, and then we're going to divide the whole thing by our new exponent. All right, so we get x cubed divided by 3, and I won't penalize you for this on your final exam, but try to remember the extra constant at the end, because if I gave you this function just like that, and I asked you to find the antiderivative. If this is just a constant, then the derivative is going to be the exact same thing as just x squared, all right? Any number added onto the end will just disappear when you take the derivative, so there's no way, based on the information I've given you, to actually figure out what that number is. So try to remember that if you can, but no worries if you can't, at least not right now. Okay, and then I tried to get a little bit tricky with you. What is the antiderivative of c? Just a constant, any number. And the answer is, remember this is technically the same thing as cx to the 0. So you could think of it that way, and then you add 1 to the exponent, so that becomes cx to the 1, and then you don't have to write that in, but it's cx to the 1, all divided by 1, which doesn't change anything. So it's still cx, and then you have to remember that there's still going to be a constant of integration. You can call it any letter. You could call it c2 or something, like with a subscript. I called it d, cx plus d. All right? There you go. And then I have 2 more. I think just 2 more. And then we'll be done. All right, what is the antiderivative of cosine of x? All right, and hopefully you guys will remember this. It is a little bit tricky to remember the trig derivatives. It is, for practical purposes right now, it's easier to just memorize the answers. The antiderivative of cosine x is sine x, or you could think of it as the derivative of sine of x is cosine of x. And I actually slipped up. I didn't include it when I sent this when I sent this as a message, but there should be a constant of integration at the end of that, all right? Because if I gave you a function sine x plus 2 and I asked you to take the derivative, you're going to get cosine of x plus 0, all right? So that is one slight slip up on my end in case Miss Christina or Miss Fiona marks it a little bit differently. Then that's my fault. All right, and then last one, I switched gears back from antiderivatives to derivatives. What is the derivative of tan of x? Now, you guys could solve this one of 2 ways. One is to memorize what the derivative of tan of x is, or the other way you could do it is you could remember that tan of x is the same as sine x divided by cosine of x. And then you could do quotient rule with that. Remember quotient rule, which is f prime g minus f g prime, all divided by g squared, where f is sine of x and g is cosine of x. Do all of that, and what you'll get at the end is that your final answer will be secant x all squared, or you can write that kind of as a shorthand as secant squared of x. All right, now remember secant is 1 over cosine, so technically if you do this whole quotient rule business over here, you should get 1 over cosine squared of x as your answer down here. All right, so that concludes your review questions. I am almost at 40 minutes now, so hopefully you guys get a chance to get through all of these questions before, before your final exam at least. But yeah, if you guys have any questions, leave a comment on the video or on any of the other videos. If you guys want me to make extra videos, then I can try to do so before I finish writing up your final exam and before you guys have to write it yourselves. But otherwise, that should be everything. I will try and make a couple of supplementary videos here and there just to go over any concepts that were fuzzy. No promises yet because my coming week is terribly packed, but I will see what I can do. Either way, I will not make your final exam something that's impossibly difficult for you guys to try and do. So hopefully it goes well. I hope the last few weeks of school have been good, and I hope you guys are looking forward to your summer break. Good luck on your test. I'm looking forward to seeing how it goes. See you guys soon.